Welcome back. In this video, we'll learn about covalent bonding. Specifically, we'll learn how to predict how many covalent bonds an element will form, which is called its valence. And then we'll learn about bond order, bond length, and bond strength. As we mentioned before, elements in the main groups tend to form bonds in order to have a completed octet. We talked about this in the context of ionic bonding. But it's also true for covalent bonding. Let's say that we have a carbon atom. Carbon has 4 valence electrons. And so in order to have a completed octet, it needs to gain 4 more electrons. So in this scenario, we're looking at the interaction between carbon and 4 individual hydrogen atoms. Each one has 1 electron. What we can do is envision the hydrogen atoms approaching the carbon, and that those electrons that belonged to the individual atoms are now being shared between them. We represent this as lines in what's called a Lewis structure. So what we see down here is carbon with 4 single bonds to 4 different hydrogens, and each hydrogen has 1 bond. Each bond represents 2 shared electrons. And so again, to reiterate, the octet rule describes how elements tend to gain, lose, or share electrons in order to have a noble gas configuration with 8 valence electrons, or a duet, a duo, in the case of hydrogen or helium. We can represent these molecules using the Lewis structures. You will very infrequently, if ever, see me writing out molecules with the Lewis dots, but rather we use the completed Lewis structures to indicate the individual bonds that exist between atoms. What you will see, however, is lone pairs being written out explicitly. And you can see in the case of nitrogen and the oxygen atoms, the oxygen atom on the water molecule, that those have lone pairs of electrons. Those lone pairs of electrons are explicitly written out. Those electrons are valence electrons and don't participate in bonding. When we look at a Lewis structure, what we're doing is showing how the atoms are connected to each other. We're also showing which lone pairs are on each element. And then we're indicating as well the locations of the shared electrons between any 2 atoms. I'd like for you to pause the video here and see what patterns you see in terms of the number of bonds that these 4 different elements make. Evaluate for carbon, hydrogen, oxygen, and nitrogen how many bonds they tend to make. So did you see any patterns? Hopefully you did. Hopefully you saw that even though carbon, for example, can be shown with multiple bonds to the same element, we have 2 bonds here, 3 bonds here. We have similar scenarios with oxygen having 2 bonds to the same element, that the total number of bonds that carbon forms is typically 4. Hydrogen is 1, oxygen is 2, and nitrogen is 3. We can summarize that here in a table. When we look at the Lewis dot structure of hydrogen, we see it has 1 electron and has no lone pairs. So hydrogen will form 1 bond. Carbon, nitrogen, oxygen, and then the halogens have a pattern. Carbon has 4 electrons, nitrogen has 5 valence, oxygen has 6, and the halogens have 7 valence electrons. So when you see these elements, excuse me, when you see these elements in molecules, we will see that carbon does not form or does not end up with any lone pairs of electrons, but rather it forms 4 bonds. Nitrogen will tend to have 1 lone pair of electrons and make 3 bonds. Oxygens will tend to have 2 lone pairs of electrons and form 2 bonds. And then the halogens will tend to have 3 lone pairs of electrons and will form 1 bond. What this does is this gives rise to double and triple bonds in the case of oxygens and nitrogens and carbons. And we see here between the oxygen and the hydrogens, we have single bonds, as is in the case of water. This molecule here is carbon dioxide. It has two sets of double bonds between the carbon and two different oxygens. And then within nitrogen, this forms a triple bond between the two different nitrogen atoms. The number of bonds that exist between any two atoms is referred to as the bond order. So for oxygen, between oxygen and hydrogen, here, the bond order is 1. Here we also have a bond order of 1. It's not really appropriate to talk about, excuse me, it's not really appropriate to talk about the bond order of a molecule because we only talk about bond orders of any two atoms. So there is a bond order of 2 here and a bond order of 2. Because carbon can form 4 bonds, it's possible that it can form various combinations of single bonds, double bonds, and triple bonds. For example, it could form 4 single bonds. It could form 2 single bonds and a double bond, 2 double bonds, or a triple bond and a single bond. Nitrogen, being able to form 3 bonds, can form any of the combinations shown here. And oxygen can form either 2 sets of single bonds or a double bond. Now, what's the effect of bond order on the properties of a bond? It turns out that bonds that have higher bond orders, bonds that have more than one bond, they're stronger than single bonds and they tend to be shorter. The bond length is the distance between any two nuclei that share a covalent bond. And the bond dissociation energy is the energy that's required to break that bond. So when we have multiple bonds, such as seen here and here, there are more electrons that are holding those two elements together. Therefore, in order to break those bonds, it requires more energy in order to separate the atoms. So if you look at experimental values for each of these 3 atoms, we see that the first molecule with a single bond between nitrogen has a bond length of 1.47 angstroms. The double bond here has 1.24 angstroms, and the triple bond has 1.1 angstroms. And if you measure the bond dissociation energy of each of these, we see that the single nitrogen-nitrogen bond is much weaker than the double bond, which is weaker than the triple bond. So that's it for this video. Thanks for watching. Have a great day.